All right, welcome back to Calc 2, and we are going to take a little detour into statistics. And I'm sorry that the homework is laid out this way, but I really don't want you to see, I really don't want to see you guys do this with Simpson's rule, because that's just insane, okay? So let me show you how we do it in statistics, and you'll be able to get a better appreciation of this because you have the calculus background. All right, so that's how we're going to do this. Is more of a sightseeing way through statistics with a nod to the fact that you guys know calculus. All right. So we talked a little bit about normal distribution, and normal distribution is, if I get the right pen, there we go. All right. The normal distribution is this thing. It's n of x, normal distribution, is equal to 1 over the square root of 2 pi sigma squared. Sometimes people move the sigma outside. Okay, sometimes they leave it inside, whatever. E to the negative x minus mu divided squared over 2 sigma squared. I never want you to use this formula, okay, ever. Now, the first thing that we do to make life a little bit easier in a statistics class is we use something called the Z transformation. And what this does, it turns every random variable, regardless of the mean and the standard deviation, into a random variable with a mean of 0 and a standard deviation of 1. Okay, and the formula we use for that is Z is equal to x minus mu, that's the mu for the x, divided by standard deviation. Okay, so say for example, if we had an x was equal to 20, we had mu was equal to 10, and we had a standard deviation is equal to, we'll do a standard deviation is equal to 5. All right, so you can look at this, right? The mean plus the standard deviation plus another standard deviation, that would be 20, right? 10 plus 2 times 5 would be 20. So let's put in the 20, right? We get 20 minus mu, 10 divided by 5. So we have 10 over 5 is equal to 2. Okay, so the z-score here is 2. Okay, the z-score is equal to 2. And all it's telling me is that this random variable is 2 standard deviations away from the mean. Okay, so all this is doing is just turning everything into the number of standard deviations away from the mean there are. And again, if we were going to use this formula, please don't. And we scaled this with mean is equal to 0, standard deviation is equal to 1, then you can see that this integral gets a lot easier, right? E to the negative x squared over 2, all right? Because this is minus 0 squared, and this is 2 times 1. So this integral, because we can pull this thing out as well, 1 over 2 pi square root, and then we could integrate e to the negative x squared over 2 from a to b. Now you still can't do this, all right? There is no elementary integral that's going to let you do it. I mean, there's a cutesy little trick which lets you multiply it by another one, and then you convert it to polar coordinates, and then you go through the whole thing. That's not really helpful because it still doesn't give you, like, you know, an answer. It's cute being able to do the whole thing and to prove that it is a probability distribution, but it's not a workable solution. And quite honestly, doing, you know, the reason why we would do this is because if you were going to use Simpson's rule on this thing and get a whole bunch of different values for different z-scores, then you would only need one curve to work with, and then you could just map other means and standard deviations into that one template. Okay, that was the whole reason, was to cut down on the amount of work you would have to do on this. Okay. There's another technique we're going to learn later in the course, which is Taylor's theorem, or Taylor series, and I think that's a slightly easier way of getting different values for this, right? And there's a reason z-score tables, right? They go up 2 decimal places. So some poor unfortunate soul, they didn't have TV then, so this is why, or internet. They would just, okay, we're going to start at z equals 0.0. Now we're going to do that integral from negative infinity from 0.1, and for 0.2, for 0.3. Okay, this is an even function. So the nice thing is that you get, some symmetry, so you can exploit that, knowing that 0 is going to be half, right? Because it's symmetric. That's probability of half. So if you figure out like how much more 0.01 is, then it's the same thing as like how much less negative 0.01 is from the mean. And that cuts down your work a little bit. It still sucks. All right, it's still very, very tedious to produce a chart like this. Okay, let alone doing it for how many problems I have you doing it on. Please spare yourself. Okay, if I didn't get to you before that, okay, I'm sorry. You'll please curse me. Okay, I'm so sorry. It builds character, but that's not enough. Okay, so if I was going to do this with calculus at this point, right, I'm looking at number 8, and I'm not going to. The heights of adult males are normally distributed. You need that to be said so that you know that this monstrosity applies. Okay, we have a mean of 69. So mean is equal to 69, and standard deviation is equal to 2.8. And they want to know, excuse me, they want to know what's the probability between 65 and 73. So in statistics class of the 20th century, we would take 65 minus 69, right? X minus mu, divided by the sigma, 2.8. And this is my z-score. Right? And I know I don't have to tell you guys how to calculate that and go through a whole thing with statistics because they will often forget parentheses, but 65 minus 69 divided by 2.8. Okay, and we're looking at, remember these always get truncated to 2 decimal places here. So that would be negative 1.432, and then we go to the other side, and we would say, what is that, 73? 73 minus 6.9 over 2.8 is equal to a positive 1.43. Okay, so again, you could use some symmetry and just calculate the integral between 0 and 1.43 and then just double it. Okay, but again, even that is way too much work, all right, to deal with that as Simpson's rule, because I have no idea how many little things you want to curve this up into, right? Certainly as few as possible. Okay, but let me show you something. Okay, you have a TI-83 or 84 calculator. By the way, I will never ask you this question on an exam. So if you're looking at this and trying to do it in Excel, I'll show you. We're not going to. You can do it. The calculator is very easy to use. All right. So here what we're going to do. You're going to go second function distribution. Okay, and you're going to hit normal CDF. Okay, the PDF will tell you what value each of these points is. We don't really care about that. We want to know the sum, right? We want to integrate this thing. That's the cumulative part. We are adding things up. Okay, and what we're going to do is we are going to go from the low number, 65, to the high number. And if you have a TI-84, you don't even need this. It'll tell you. Okay, it'll tell you which the low number, which the high number. Then it'll ask you for the mean, excuse me, and then it'll ask you for the standard deviation, 2.8. Okay, it's going from, I know it's going to be more than 68.68, but it's not going to be huge. Okay, it's not going to be close to 1. Okay, 0.84. Okay, that seems about right. So this integral here is 0.847. Okay, that's what I want you to do. At the very worst, you can do the Z transformation thing, and we can type this in, and we go to second function distribution, normal CDF. Now remember that this is for, right, this is for mean of 0 and a standard deviation of 1. So we're going from negative 1.43 to positive 1.43, 0 to 1. Enter, done. Okay, same. Well, I I rounded, so it's going to be a little different, but you know, 3 decimal places, it's the same number. Okay, it's 0.847. Right? And that is how you should be doing these problems. Okay, I will never ask you to do one of these by hand. Okay, it is nice to look at it and say, oh, how did they get the numbers that come out of the calculator? By Simpson's rule, okay, or by Taylor's formula and doing it that way. But we do not we're not doing Simpson's rule for a whole bunch of problems here. That isn't going to help you with anything. Okay, it really isn't. And I'm sorry that if you did it, I should have gotten this earlier. But yeah, feel free to, you know, you should probably, you know, exchange your soul to have mine and have a bad thing to it. All right. What percentage of male population is more than 6 feet tall? Okay, so let me tell you something about the normal distribution here. Once you get outside of 3 standard deviations, this is a really, really tiny number. Okay, so the area after 3 standard deviations is almost nothing. So if you go 4 standard deviations out, 5 standard deviations out, that's a nice upper bound. You don't have to go to like a gazillion. Okay, the statistics book would have you do it this way. They would say, okay, well, we're going to do norm CDF in your calculator. Your low number is going to be 72. 6 feet is 72 inches. And then you can't type in this, right? The calculator does not have infinity. So what they tell the statistics people to do, right? They do the stats class, is they say 1e to the 100. So 1 times 10 to the 100. That should be a big enough number to approximate infinity. It's way too big. You don't actually need that. Okay. You know that 2.83, right? 2.8-ish is a standard deviation. So if I go up 3 standard deviations, okay, if I go up to 9, the area after that is going to be almost nothing. So you don't need to do all of this, right? We're going to say 72 plus 9. What do we get? We get 81. Okay. Round it to the nearest easy number you can. Go up. Okay. It's always more useful to move up than it is to move down. Okay. So always round it to the next easiest number you got. You want to put it 100? Be my guest. Put it 100. You want to put in this? You can. I'm not going to yell at you. But you're working a lot harder than you really need to be. Okay. 72 here. And then what was our mean? Our mean was 69, and our standard deviation was, what was it, 1.8, 2.8, right? 2.8. And that'll be fine, okay? So let me just show you, okay, on a calculator. We're gonna do both ways. We're gonna do to 81, we're gonna do to 100, and you can see like how different they are and realize they're really not that bad. Okay, so enter. So the 72 is always going to be there, right? Because my mean and standard deviation are both in inches. We're using inches. And if I go up to 81, okay, and our mean is 69, and our standard deviation is 2.8, okay? So this is the integral, right? The integral from 72 to infinity of e to the, you know, we'd have to put in the mean and the standard deviation into this. This is not going to be a fun deal. Okay. Or we could have done z-scores and just use 0 and 1, which would be a smarter way to work. All right. We ended up with, seems like a lot. Okay. But we ended up with point, what do we get? 1420, 1419. Right. Now, 142, 0.142. All right. Now, I'm going to do normal CDF distribution. Right. Same idea. We're going to do 72 inches. I'll go to 100 this time. You can go to 1,000, but I'll go to 100. Oops, I did go to 1,000. Okay, mean 69, standard deviation 2.8. Okay, and with 3 decimal places, 0.142. Okay, again, my stat students, they don't trust me. I'm like, no, we don't think you know how to use a calculator. Okay, that's all right. They'll trust the book, and I get it. You know, I did this, I use the book too. So it's 1, and then in a calculator, it's a TI to put scientific notation in, it's second function, and then this EE button. Do not go to alpha and type in E. That is a different E, okay? Just like little e is Euler's number, capital E, or the E here is like you're going to spell a word like we, and then this one is times 10 to the, okay? 1 E 100. What's that mean? Mean is 69, standard deviation 2.8, right? Oops, what did I do? 2.8. I have to type it in again. Shoot, sorry. So norm, CDF, I talk too much. Okay. So we have 72, 1, EE. Oh, maybe it was 99. Maybe that's it, because it doesn't let me do the whole way. Okay. So 1 times 10 to the 99th. Missing a whole lot there. Mean is 69. Standard deviation was 2.8. Right. Almost the same number, right? 0.142. Done. All right, so that's what we're doing with this one. Okay. Next one. Okay. Boxes are labeled as containing 500 grams of cereal. The machine filling the boxes produces weights that are normally distributed. See, there's that word again. If the target weight is 500 grams, then the probability that the machine produces a box with less than 485 grams of cereal. Okay, so how are we gonna set this up? Right. So technically, calculus-wise, what we're doing is they want 485 or less. Okay, and then we're going to type in the mean and the standard deviation. It'd be the 1 over 2 pi sigma squared, and e to the negative. Maybe you changed, right? Maybe you changed 485 into a z-score, so you could just use 0 and 1 here. But either way, right? This is x minus 500 squared over 2 times 14 squared. This looks delightful. We have to integrate that. We're not doing that. All right, we're not doing it. So we're going to do norm CDF, okay? And we're going to go from a negative number. And again, just what is a small number from 500 if you have to take steps that are about 15? So 3 times 15, right? Well, it's 14, right? But we're going to call it 15 for the sake of making this easy. 3 times 15 is 45. Let's call it 50. I don't want to do arithmetic. So we're going to go from 450, right? Oh, to 485. Right? You could type in 0 here, okay? But 450 to 485, and then my mean is 500, and my standard deviation is 14. Okay, so let's see what that is. Okay. It's going to be, yeah, about there. So that's 16, 15%-ish, 14, maybe 12%, something like that. So we're in that ballpark. Okay. If you had statistics in high school, you probably learned about something called the Empirical Rule. I got to admit, I met one student who was able to, he pretty much did my entire class just with Empirical Rule. It was impressive. Okay, 14%-ish, right? 0.142. Okay. What if I did this a little bit differently? And I said distributions, and instead of putting in 450, I'm going to be real lazy. I'm just going to put a small number in. How about 0? Okay, up to 485. Parentheses, okay, 514. Okay, again, 0.142 to 3 decimal places. This is fine. Okay, so again, I really don't want you to run around doing Simpson's rule on this. It's been done. Okay, back in the day, we had CRC books. they would carry out all of these calculations for us, and they wrote them down. Our job was to look them up. Okay, your job is to punch them in the calculator. Right. So this one, suppose the law states that no more than 7% of manufacturer's cereal. I don't know how you're supposed to do this in the calculus book. Okay. Suppose the law states that no more than 7% of a manufacturer's cereal boxes can contain less than a stated weight of 500 grams. At what target weight should the manufacturer set its filling machine? So here's what we're doing, right? We want no more than 7%. Okay, so we want negative infinity up to limit m, pick a number, of n of x with the mean and standard deviation here, dx, to be 0.07. That's what we're trying to figure out. I have no idea who wrote this problem or why they thought this would be a good idea. Again, it's stats, is not that big of a deal. Okay, what we're going to do, notice that in the CDF, we fed it two numbers and it spat out, right, a probability. Okay, the symbol we use for normal distribution in the more advanced stats classes is this is a phi. Okay, and this means a standard normal. Okay, so we would take, we have to put z-scores in for this, all right? But all this means is we looked it up on the table. So we have a 5, we're going to put a number in, right? And that's going to give us a value. Okay, if we put phi of 0, 0, 0, 0, okay, phi of 2 is going to be 0.975. All right. Now, notice that this looks a lot like a function. Like if I took the sine of an angle and I got a number, 0.4431, how would I get the angle back? We would take the inverse sine, wouldn't we? We sure would. So we would find the inverse sine of 0.4431, and that would tell us what theta was. Guess what we're going to do with this one? We're going to take inverse phi. We're going to do what they call the inverse normal. All right, we would say phi inverse of 0.975, and that would give me 2. All right, so let's see. So we're going to do second function, distributions. We're going to go to inverse norm. Again, if you have a T84, you're going to be in a much easier world than I am, because I got to remember which order this stuff goes in. Okay, 0.07, we put the probability in first, then we put in the mean, 500, and the standard deviation, 14, and it's going to tell you what the x value is for all of this. Okay, 479, did they make us do a decimal place? I don't know. Hopefully not. Okay. There's gram, 4789, done. All right, that's it. All right, let's do one more. All right, let's do number 10. I'm sure that, you know, and honestly, I would never ask you any of these on an exam. It's just not, you know, it's like we could do tourism of statistics with the calculus mindset. You're not going through and doing statistics here, okay? It's just supposed to be a taste of probability. It's not supposed to be this intense. Okay. Oh, okay. Why don't we do number 11? Okay, because it's a different kind of problem. So it says for any normal distribution. Okay. So here's a little tip. I get this in physics classes all the time. Okay, they give you something and they say, okay, figure out what the force is or whatever's going on, and they didn't give you the mass. And you go up to the teacher and they'll say, I think you forgot the mass on this thing, and then they smugly tell you it doesn't matter. I'm like, okay, look, I knew there was 4 formulas I was supposed to memorize for the test, but I only memorized 3, and they all have the mass in them, so it doesn't matter, huh? If it doesn't matter, it's your choice. You put in whatever you want, because if it doesn't matter, your choice is irrelevant. And it usually is. I mean, they'll drop out right? You'll get an m over an m, and then it didn't matter if you picked 1, 10, 1,000, or pi over 6 grams, or kilograms, or whatever. This is the same thing. For any normal distribution, find the probability that a random variable lies within 2.5 standard deviations. That means this integral, right, is going to be negative 2.5 to positive 2.5 of my normal distribution. All right, that's what we're trying to do. If they said for anyone, and you need to pick a mean and a standard deviation, why don't you pick an easy one? Okay, that way you don't have to worry about like what's going to drop out or what isn't. Okay, pick one that's going to make your life easy, like 0 and 1. Standard deviations always have to be positive, by the way, so don't pick one that's hard to work with. Okay. So yeah, all we're going to do is we're going to use a standard normal. We're going to say normal distribution between negative 2.5 and positive 2.5 and call it a day. So if we're going to go back to distributions, second function, distribution, CDF, enter, and we want negative 2.5 for my low part, positive 2.5 for my high part, 0 and 1. All right, this should be a pretty high number. It's not going to be 0.95, I think, but, oh no, it isn't. Okay, 0.9, there we go. 0.986. Okay, and that's what you're supposed to do with these. So please, I hope I catch you in time before you've gone off and run through all of these problems. If not, I will take whatever bitter thing you want to say to me because I deserve it. But if you haven't, then good news for you, you don't have to go through that pain and that horribleness, okay? I think I gave my negative x squared over 2. I think I give this one to people, just this one, and it's like between x is negative 3 and positive 3. I say delta x is equal to 1. Okay, so I think that's as close to like figuring out a normal distribution as I've ever come to anybody rather than making this happen. So this one is pretty fair, right? And I'll say 1 over 2 pi at the end here, so that they can multiply by it and get normal distribution like. But what this book went into for this was just way out of bounds, I think. And I'm really sorry if you did that. Okay, so we're going to stop here. That will conclude 8.5, I believe, and I will get started on chapter 9 and put those up so that you can have a guide for those. Okay, take care, and I will see you next time.